So maybe go back to 15 and maybe a little bit go through what goes to your model. I've asked that later, so not here. So pause. What is really going to your model? Two-level system of the dot, discrete levels of phonons, then a sea of the path of other phonons. Is that what it is?
Right, so
540.
the torsional modes, they in a sense address
Yeah, you're back.
1s exciton transition. So
Yeah,
this is the
sorry,
lowest
I
energy,
can't see.
lowest
How is
energy
it
transition.
included to the model?
Yeah.
What?
How is it
Do you
included?
deal now? Yeah.
So do you have a
Oh, this is
you
just,
have you have two-level system and then you have other levels for the torsional modes.
right, so
You couple those.
this is incorporated just by harmonic coupling in terms of a vibrational coordinate. So in this case, the torsional mode, whatever vibrational coordinate it is. So this is just a general thing where, general model where for small amplitude vibrations, you just approximate as harmonic coupling.
And the path, do you do it with a, do you use some master equation approach to include that, or do you have really many harmonic oscillators?
So this is in the cumulant expansion. So we truncate the cumulant expansion.
So you write so you start with some certain Hamiltonian.
Right.
You don't have a backup slide how the Hamiltonian
Oh.
looks like? Well, we can talk about that later.
Looks like eight.
Yeah, I have an appendix in my thesis. That, yeah, I should have had back some equations. Yeah. Oh. Yeah, so here are the cross-out slices for the experimental simulated line shapes. And you can see that the simulation reproduces the two main features of the experimental spectra, which are the growth of the pedestal with temperature and these two sharp peaks on either side of the zero phonon line. And just for comparison, here absorption of fluorescence spectra simulated with the same simulation parameters. And you can see that the vibrational line shapes are much more prominent in our data compared to the linear spectra due to this nonlinear enhancement of vibrational line shapes I talked about earlier. And just to show you quickly our simulation parameters, the spectral density that we use has this functional form, which is derived for a spherical quantum dot. And there's three parameters. So the first parameter, P, can either be 1 or 3, depending on whether the acoustic phonons couple via the deformation potential or piezoelectric coupling mechanism. And we found that we were only able to achieve good agreement between experiment and simulation by assuming piezoelectric coupling. And the second parameter, A, is the amplitude of the spectral density, which determines the size of the pedestal. And omega C is the cutoff frequency, which determines the lateral extent of the pedestal. And for this discrete mode, we use our calculated energy of 0.8 MeV and a Poisson factor of 0.6, which quantifies the electron-phonon coupling strength.
So your cutoff is a millivolt, and you've got like sidebands going out to 10 millivolts.
Right. It doesn't.
What's going on?
There's
there?
not a direct. There's not a. I guess there's not a direct correlation between those two. Well, there's a direct correlation, but the numbers don't directly correlate.
So the light that's coming out at minus 10 millivolts, does that involve many phonons? Is this a single phonon sideband, which has a very broad line shape, or is this? I'm not getting. Or is it many phonons involved in that emission?
Never thought about it in terms of those terms.
Because you're saying, but when these single dot luminescence, right, showed multiple phonon sidebands, so you could see 1, 2, and 3 phonons being involved.
Those are optical phonos.
Those were optical.
Yeah, those are not continuum.
I think the answer is that there's multiple. So the harder you drive vibration coordinate, the more replicas you get. And so you have that, plus you have a continuum of phonon energies because they're acoustic phonons. Right? So you have to, it's everything just gets all smeared out.
So in your theory, you go to the two phone level, right? You set up to cluster or humans up to second order. Is that what you're having?
Right.
Yeah.
But
That one includes only things up to the first or the second phone side. So I think if you can model it like this, I think the higher order can process are.
I would think, you know, so we've seen data similar to that in quantum models, very much like that. And the fact that the zero phonon line is so narrow, it tells me at least that it's moving along compared, that it's decaying into states that are getting re-excited. So it's you have decay of the diagonal matrix elements at one frequency to another frequency. And then you're probing, the third pulse, you're probing that exciton state. So that, in other words, that would be your phonon is shifting the energy down or up. And your third pulse is probing that new state. But the scattering is occurring in the diagonal matrix element. It's affecting your off diagonal too, the dephasing, but it's a slow process, I'm guessing, because your zero phonon is so narrow. So in other words, it looks like a form of spectral wandering or spectral diffusion. And I'm wondering, how do you rule that out? It's not saying, I don't know that it says anything that your model is incorrect or anything. I don't quite understand how your model is included and how it shows up in the density matrix. But that's, so let's see.
yeah, I'm not sure how to think about the interplay between the off
You
diagonal.
know, a T1, I forget what you guys call it, but when you vary, I guess it's big T. Did you do that also? Did you see a fast decay and a slow decay in that system, or at least a high exponential?
No. This is
Your-
simply, in fact, it doesn't decay very much because the population time in these nanoseconds are nanoseconds at least. In fact, they're beyond our stage now.
What's the dephasing time?
So it's over 50 picoseconds.
When you said the lifetime is nanoseconds, is that the radiating time, or is that the T1 time that's measured at the same?
That's true. That is the radiated lifetime.
So that's not necessarily the state lifetime.
Right. So,
That-
and there is
that
fine
makes
structure.
sense. Huh?
There is fine structure where you do have non-radiated relaxation.
No, I don't mean, well, I just mean that I don't think it's not radiated what you mean. I mean non-radiated in the sense that the phonon shifts the energy. And now it radiates or you go at a different energy.
Right.
It's like a scatter. You know, just imagine you had a free atom and it was Doppler, you were on resonance, and then it underwent scattering to another velocity. The Doppler shift would change.
Oh, so
And then you broke it into
Completely
the
tells
velocity.
the cross diagonal like
I know.
it completely tells you exactly what you just said.
So another thing is, so this data is taken at a capital T of 1 picosecond, and if we took some data at over 10 picoseconds, and we don't see any significant broadening of our lines, which would I think would correspond to what you're talking about.
So the fact that it's cross diagonal says it absorbs one frequency, believe it or not.
It says what?
So if you go out here at minus 10 MeV, that says it absorbs one frequency and believe it or not. Exactly what you said.
Well, that's right. Yeah, I mean, it absorbed it. Of course, I look at this maybe a little differently than you do, but it is emitting at that place because you're probing it at that frequency. So you're creating the off term, it's that, it's the same thing.
But I mean, you gotta be careful, don't think about this like luminescence or.
Oh, no, of course not, I'm not.
I think it's completely, there's nothing, it's completely consistent with what you said.
But if that would mean that it was a spectral diffusion effect, so the decay,
Yes. Yeah, I mean, it's definitely just.
but it's, okay. Well, now I understand. Okay.
Right, spectral diffusion and it is sort of the underlying mechanism of the phasing.
You read Schultz.
Who? Absolutely not. Hasn't he read Vermo?
Read Schultz's book and come back.
We did the work before he did it.
But the point is that dephasing and spectral diffusion are the same thing.
No, no.
I mean,
No, even NMR calls spectral diffusion T3. It's a T3 process.
But a fluctuating energy can look like spectral diffusion and also look like diffusion. That's what this is.
If T3 contributes to T2. But anyway, I don't know, this is the battle of spectroscopy. This is good fun, don't worry about it. It's not relevant.
Yeah, so just as one last check, we want to see if there's, if many body effects, in particular by exciton resonances, are distorting the pedestal feature that we're trying to characterize. So we do this by phasing our 2D spectra by maximizing the real quadrature and comparing the experimental simulated quadrature 2D spectra, which I think agree pretty well. And you can see this from the cross-diagonal slices as well, where we don't see any strong bi-exciton features that would show up as negative peaks in the real quadrature. And you can see this from the phase as well. And accumulation effects should also not be an issue, since from our calculations, we're exciting at our excitation densities 0.2, less than 0.2 exciton per nanocrystal. So that was the end. But yeah.
Final question on that. So if you take that model that's fitting your data, and maybe you're not allowed to do this, but you crank up the temperature,
Yep.
do you account for the Stokes shift that you see in just good old-fashioned absorption and PL spectrum?
So in the nonlinear spectra, the Stokes shift, we don't see a Stokes shift because we're not on the time scales of the lattice rearrangement. So
I think he's asking if your model predicts the Stokes shift, you see a linear response.
Yeah.
yeah, it does. So so if you look at the simulated absorption fluorescence spectra, you do see a Stokes shift.
And is the same value that you showed in your very first plot?
No. So
That's my
that
question.
yeah. So there's other things other underlying mechanisms of a Stokes shift though. It's well known in these nanocrystals that there's fine structure. So the way that you emit light after absorbing a photon is you first non-radiatively relax into a lower lying dark state. So there's an energy gap there as well that contributes to a Stokes shift. And I don't think that makes up the difference.
So is the Stokes shift understood in these materials?
It's definitely still an active field of research.
So I don't feel bad that I never knew where it came from.
Yeah, so I know in general that there's generally two main mechanisms for it. It's after the absorption, there's a different potential energy surface for the electronic excited state. So the lattice rearranges to lower the potential energy, and then you emit at a lower energy. And then the other is the exciton fine structure. But because we didn't do any, I guess because we were just focusing on the nonlinear spectrum, we focused on characterizing the pedestal feature instead of focusing on the Stokes shift. But yes, in our model, we do see a Stokes shift. Yeah, so that's the end of my section on acoustic phonon coupling to excitons. So now I'd like to discuss our other main result on these nanocrystals, which centers around optical phonon coupling to excitons. And these results are published in this reference here. So we can go back to the one quantum spectra and focus on a different set of features, which are these sidebands on either side of the main pedestal. And if we take a cross-diagonal slice, we see that these sidebands are located at plus and minus 26 MeV, which is precisely the longitudinal optical photon energy of cadmium selenide. So you can understand this in terms of this displaced oscillator model that I talked about earlier, as absorption and emission in and out of the different ladder states separated by the yellow photon energy. And if you remember, our second pulse can induce intraband coherences between states close in energy. So if coherences between the ladder states is possible, we should see something happen as a function of capital T as well. So what we do is we take one quantum vector as a function of capital T and Fourier transform the complex values of the sidebands. And what we find is that the Stokes sideband exhibits strong quantum oscillations at the yellow photon energy, which indicates coherences between the ladder states. And I want to mention that this one-sided spectrum, which consists of only a negative energy peak, is a strong indication of intraband coherences between vibrational states. So if the states were electronic in nature, you would see a positive energy sideband as well.